Everyone, I'm Munia Ferdoushi. So today I'll be presenting on the fully printed sensor-based extended field effect transistor for monitoring of potassium and ammonium ions. So in our lab, we basically work on developing wearable devices for health applications. So when developing these sensors, the main things we focus on are first of all, the sensors have to be skin conformal so that they are comfortable to use. They have to be private, and also we care about multiplexing so that we can use multiple analytes on the same sensor. We want to make the sensor personalized and also want them to be capable of making the data available for the user. And mostly since biosensors are usually have a very short lifespan, we want to make them disposable, so making them cost efficient is a big aspect. That's why we are here in our lab, we work on flexible hybrid electronics. So what we try to do is that we use a conventional MOSFET technology, CMOS for the analog front-end signal processing and data transmission, and for the sensing part, we use printed electronics and electrochemical sensing. In this way, we are able to get the best use of both of the technologies that are available to us. So here I'm showing the application of potassium and ammonium ion sensing, why it is important. So potassium is very important in a lot of diseases, including cardiovascular diseases and stroke, diabetes, and also hypokalemia and hyperkalemia have some significant impacts on the patients, and ammonium specifically is very important in renal diseases, chronic kidney diseases, and end-stage renal diseases. So it has been shown that if the kidney stops functioning properly, then it does not break down the urea. As a result, there will be excess ammonium ion in saliva and other bodily fluids, and this sometimes causes the ammonia breath. In people suffering from CKD, the ammonium ion concentrations can change as much as 10 times, and sometimes CKD also results in change in potassium concentration. That's why in this study we are focusing on these two type of ions to detect. So for our sensing, we have two sides. The analog front end is a printed circuit board, and for the sensing part, we use printing. So we print gold counter electrode, gold working electrode, and silver chloride reference electrode using our printers available in our lab. Then on top of gold, we deposit PEDOT PSS layer for improved charge transport, and then we have an ion selective membrane on top of the working electrode that facilitates the ion detection. Finally, we use a technique called extended gate field effect transistors for measurement of our ions. In industry, usually the most common printing technique for inks is gravure printing. It has very high output and it is very cost effective. But for prototyping in lab, we usually use inkjet printing or extrusion printing. So we have inkjet printer that works well with low viscosity inks like gold. So for printing gold, we use inkjet printer on the right. And for printing silver chloride, we use a Voltra Nova printer. It works better with inks that have high viscosity. Here is a demonstration of how the printing process looks like for printing an array in our lab. And after printing the gold electrodes, we deposit PEDOT PSS, and on top of that, we need the main sensing element is the ion selective membrane. And so the ion selective membrane needs formulation based on the constituents of this membrane. The main component is the ionophore, and this ionophore is embedded in a PVC matrix. For our application, we use valinomycin for potassium ionophore and nonactin for ammonium ionophore. In order to improve the mechanical properties of the ion selective membranes, we used plasticizers. So the plasticizers reduce the glass transition temperature of the PVC matrix, and for our task we use dioctyl silicate. Uh, we also need some kind of ion exchanger in the ion selective membrane that facilitates the transfer of ion, because uh, uh, there are neutral ionophores and positive cations inside the ISMs during detection, and there needs to be some kind of anion to balance the charges. For our purpose, we use potassium tetracates as the ion exchanger. And after the sensor fabrication, we have to do the interfacing with the analog front end. And here we use a technique called extended gate field effect transistors. So this is the structure of a normal conventional transistor, where we have the source and drain, and we have the silicon oxide and a metal gate, and we provide a bias to the gate that modulates the channel properties, and we get the current, drain current that we can measure. So in order to detect, in order to interface this system with liquid solutions, there was the research developed ion selective field effect transistors. In ion selective field effect transistors, instead of having a metal gate, we have a solution in contact with the silicon oxide or any dielectric in the channel region. And then we have a silver chloride reference electrode embedded in the solution. The problem with the ion selective field effect transistors is that it is very hard to find dielectrics that are compatible with this kind of any kind of solutions, and so there has been research on finding good dielectrics. Also, we have to have some encapsulation so that the source and drain regions are separated from the solution. And also, because it's everything is in a single unit, if either the sensing element fails or anything happens here, the whole thing becomes unusable. So in order to solve this problem, there was the development of extended gate field effect transistors. So here we have a normal a MOSFET transistor, and we extend the gate to interface with sensing unit. And this sensing unit can be of a variety of form. In our project, we are using ion selective sensing unit. It can be other things also. So basically, the sensing unit is in series with the gate, and the potential developed across the sensing unit is modulating the charge of the gate or the voltage of the gate. And based on, so as a result, we have a different turn-on characteristics of the transistor. Practically what we see is that the threshold voltage is getting modified, and this causes the output current to change, which can be detected with our circuits. So these extended gate systems are not only good for measurements of potentiometric sensors where there is a potential developed, they have been shown to have good correlation with impediometric sensors like here. And the best part is that because the MOSFET portion is coming from conventional technology, there can be a lot of development of the sensing unit. So different groups are trying different sensing methodology. Here, they're using graphenes for cortisol detection. Here, they are using quantum dots and also microneedle-based sensing. In our lab, I personally have been using this kind of extended gate measurement systems also for cortisol, dopamine, and serotonin detection for other applications in health. So basically, this is the block diagram of the whole sensing unit. This is the printed circuit board. It looks big because it has a lot of other functionalities like photoplethysmography and then electrothermal activity. But this part is very simple. Here we have a PMOS transistor, and this PMOS transistor's gate is in series with the sensing unit. So this is the reference electrode, and this is the working electrode that has the ion selective membranes, and the solution is drop casted or this thing is immersed into the solution, or ideally it would be placed on the skin for sweat sensing or in touch with saliva. So using an analog to digital converter, a bias is applied at the working electrode, and basically the potential developed across the working electrode and the reference electrode is modulating the bias that is applied. As a result, the threshold voltage of the as a result, the turn-on characteristics of the PMOS changes, and there is a simple comparator circuit here that compares the drain voltage of this PMOS with another applied voltage and gives an output here. And we have wireless, we transfer the data wirelessly here. So here you are basically seeing an inverted current voltage characteristics because we are actually measuring voltage instead of current. So that's why it's inverted. And simplify, what happens is that the gate voltage is basically the applied bias minus the open circuit potential that is developed. After experiments, we get this kind of IV curves. These curves are basically as here the concentrations are mentioned. So as the concentration is increasing, the curves shift inwards because the transistors are turning on faster due to higher potential developed due to higher concentration of ions. How to determine sensitivity, what we do is we fix a certain output potential and get the sensing voltage at that potential. And this is the bias signal, which is actually the output based on the concentration. And we get the Nernstian log linear response from here. In order to know that the sensors are actually giving accurate results, I compare our system with commercial potentiostat. This is a PalmSense 4, and the results are actually pretty cohesive. So that's how we know that the sensors are working, and they give a good coefficient of determination. And the effect of PEDOT PSS is actually very important because without PEDOT PSS layer, I was seeing that the response was getting saturated or going in a reverse reaction at a higher concentration of ions. But when PEDOT PSS layer is used, because it facilitates electron and ion transfer, the range remains linear for a longer range of concentrations. Also, I studied the selectivity of our sensing system, and both potassium and ammonium ion sensors are quite selective to interference. Here, the sensitivity is shown for sodium, for potassium, ammonium, and sodium, and also for ammonium, sodium, and potassium selectivity is shown. And here are the results, and all of the experiments done have very good coefficient of determination with more than at least 95%, and the inclusion of PEDOT PSS improves the range of linear concentrations. And this is the current status of the work. What I'm trying to do is, instead of focusing on the electrochemical methods of improving stability, we are using differential extended gate structures to improve the stability of this device so that the sensing system functions for a longer period of time. And I'm also implementing this system for detecting other biomarkers of health and specifically mental health like cortisol, dopamine, and serotonin. And this is our lab group. I would like to thank the IEEE Sensors Authority for giving me the opportunity to present. Thank you, everyone.